start this recording. Okay. Okay. So, hand it back assignment 1. Overall, looking really good. Just a couple of things. I do write a lot of comments. I spend a lot of time writing comments for you guys. So just make sure you take the time to go through it, look at the feedback. And the reason that I do that, and maybe I'm a little bit harsh on the marking on assignments, I say that, but I'm not really, is because it's better that you kind of get knocked down on an assignment that's not worth very much, and then you'll know exactly what to do on the test, right? So I do kind of try to keep you guys under control on the assignments, right? Because they're not worth very much, right? And then we can get these kind of silly habits over and done with on the assignments, right? Assignment 2 is due on Wednesday, right? Beginning of class. If you didn't get a printout, I'll grab some photocopies after class, but otherwise it's posted on Moodle, so just come see me after class if you need a copy of assignment 2. Okay. This morning I nearly forgot that we hadn't finished the tree diagram question from 2.2. So what I want to do is just go back and finish that, because that's basically what you need for question 2 on assignment 2. So this morning when I was doing it, I was like, oh no, we're done chapter 2, that's it, no more. And then they're kind of saying, well, what about all those questions we didn't finish? Oh, right. So you want to know more, huh? All right. So where we finished last day, and I'm just going to tack this onto the notes that we did last day, and then I'll start a fresh sheet for today. We had this situation where you can either get an A or not an A on the midterm, and then you write the final and either get an A or you don't get an A. Right? And so we developed this tree diagram where M represents an A on the midterm and F an A on the final, ironically. And then we had, so the midterm layer, the final layer, or the final exam layer. And then what we said was to find the probabilities at the end of each branch, we just multiply down the branch. Right? And so this and this gets us to the end of the branch here. So last day we developed all these probabilities, but I'm pretty sure that's all we did. It is. It showed those calculations. On the assignment, because I've had a few questions already, so on the assignment, it's not this complicated, right? It's actually an easier version of this, where you go out on this cruise and you either have a sighting, so a whale, dolphin, whatever you're going for, right? And so it's a whale watching cruise, so you have a sighting with an 80% chance, and you don't have a sighting with a 20% chance. It's either have a sighting on the first day or you don't. So because these are consecutive events, right, on the assignment, what you're going to have is you're going to have day 1, day 2. Right? So even if you have a sighting on the first day, you go out, it's a new day, second day, you have a sighting or you don't have a sighting. Right? Same thing here. So that's how those two are related. But I don't want you to overthink it, because now we're just talking about, did you have a sighting or did you not have a sighting? So, we spent a lot of time building this tree diagram, right, last day. And so on the assignment, they're each worth 2 marks. That's not really the case on the test. The tree diagram should be worth a lot more, right? Because we do all that work building the tree diagram, and then these questions kind of just fall out, right? So the marking scheme's a bit off on the assignment, but that's okay. It's to get you guys higher marks. What's the probability? So question question 2, what's the probability of a student earning an A on both the midterm and the final? Right. So now that we have our tree diagram, we can say, okay, well, we have to have an A on the midterm, so we have to go down this branch. But then we also have to have an A on the final, so this is the only branch that satisfies that. And we know that the probability of ending up here is 0.0611, because that's what we calculated last day. So in terms of the answer for question 2, the probability of M and F, which we were actually just writing the probability of MF, cutting out the and, 0.0611. So once you have your probabilities in your tree, you can just pull those probabilities. You don't have to recalculate them or anything like that. You can just say, well, it's 0.0611, moving on. Right? So that's nice. So spend that time making a nice tree, and then you can just pull information from it. Oops. Three. Oh, and it's feast or famine around here. I either don't have enough printouts or I have too many. So I do have 3 extra copies of the chapter 2 notes. We're done with these, but if you didn't get one, then come grab one after class. It's a lot of printing. So question 3, what's the probability of a student earning at least 1 A on either the midterm or the final? Right. So now we want to know, let's just write it out here. The probability of at least 1 A. The probability of at least 1 A. So now we have to look at the branches that satisfy that. Here we go, an A on the midterm. Right, so it doesn't matter what happened on the final. We have at least 1 A. In fact, at the end of this branch, we have 2 A's. Right, here we have 1 A, right, because we got an A on the midterm, but not on the final. Right, so both of these satisfy the at least 1 A criteria. But also, if you didn't get an A on the midterm, you can still get an A on the final, and that's at least 1 A as well. The only time that we haven't satisfied that criteria is when we don't get an A on the midterm and we don't get an A on the final. Right? This one, and this one, those are all at least 1 A. And so what we can do is we can say, well, that's going to be the probability of the midterm and the final, plus the probability of the midterm but not the final, plus the probability of not the midterm but the final. I'll need some room here, but we know all these probabilities. Yeah. Yes. The answer is yes. And we'll get to it. 0.0611. There is an easier way to do it. Right. But I want to show you both ways because sometimes one of the ways doesn't make sense. Right. It just depends on how you think about it. And so I'll show you this one because it's more kind of mechanical. And then I'll show you the sneaky way. Right. So 0.0611 and the next one, 0.0689, I think, plus 0.0957. Which I didn't bring my Martha Stewart notes for these, so we'll do it again. Oh well. 0.0611 plus 0.0689 plus 0.0957, 0.22 0.57. So that's the probability of at least one A. One thing to keep in mind here is, or one thing to help you manage these probabilities, right? Because earlier we were multiplying, now we're adding, right? And so whenever we're saying or, right? This, or this, whenever we're saying or, you're gonna be adding. Right? Whenever you're saying and, or catch yourself saying and, right? This and this gets you to the end of this branch. Right? This and this gets you to the end of this branch. Right? That's when we're going to be multiplying. So just as a quick check, right? If you're saying and, you're going to be multiplying down the branches. And if you're saying or, you'll be adding up these branches. Okay. So let's do a little note here to the plus sign, because we're saying or. So just a note. When we say or, we will multiply probabilities and when we say and, wait, no complaints out there? Just a little confused. That was a test and you guys failed. No. I'm asleep at the wheel. That's what's going on. When we say or, we'll add probabilities. And when we say and, yeah, I'm going to commit to this one, we will multiply the probabilities. Multiply the probabilities. What a not helpful note if I write down the wrong thing. So this is kind of I think of it as, you turn through, so you say this or this or this. Those are all the situations that satisfy that criteria, right? And you have one on your assignment too. I think it's, part C. What's the probability of a sighting on at least one day? Right, same situation. Another way you can think about it, right, is to say, well, the only branch that doesn't satisfy that criteria is this branch here, right? We said last day that the total of these probabilities has to add to 1, right? Because we're looking at all the possible outcomes, and just by a fact of the sample space, right, all the possible outcomes, those probabilities have to add to 1, right? And so we can say, we can use the fact that they all add to 1, and then we can say, well, this plus this plus this has to be the same as 1 minus this one, right? The one that we're pulling out. So another way to find, and I'll start it down here, the probability of at least one A is 1 minus the probability of not an A on the midterm and not an A on the final. Where this probability, that's the complement of at least one A. This is the complement of at least one A. It's going to be 1 minus think 0.7743, yeah. And you can check it, but it is going to be 0.2257, right? Which gets you to that same probability. And this little trick isn't going to be that relevant for this section, but we will start using it when we get into binomials, which is next week. And so we will use that kind of trick of saying, well, I could add all these up, or I could just do 1 minus this one out here, right? Just makes it easier. Right? So just getting used to thinking about it that way, right? It could just be all the probabilities that you want added up, or 1 minus the one that you don't want, right? Pull it out of the probability. So, any questions about that one? Oh, okay. I think there's one more little part here. 4, what's the probability of a student earning an A on the final but not on the midterm? So 4, we want to know what's the probability of, we've listed first the midterm probability and then the final, so I'll keep that same order. And what was it? A on the final but not on the midterm? Is that the question? Yeah. So you can't get an A on the midterm, but you have to get an A on the final. If we look at our tree diagram, there's only one way that can happen, right? We can't get an A on the midterm, but then we have to get an A on the final. So the probability that we're looking for is just the one at the end of this branch here, 0.0957. Okay. So sometimes it's just one of these branches that you're looking for, and sometimes you have to look at which branch satisfies this criteria. And this is 0.0957. Nice. Any questions about that? So I'll just repost these notes over the old ones that I posted on Moodle so that all the information's there on this sheet, so it's all together. And then I'll start a new sheet for today. Oh yeah, I'll just make a note here that assignment number 2 is due on Wednesday. I've been getting a lot of questions about this assignment, and it is a tricky one, so don't worry about it. I just kind of worked through it. I'll be here all day tomorrow. It's not office hours or anything, but just want you to know that I'm around tomorrow if you have questions. And so I am around tomorrow. All day. I can definitely commit to 9 to 5. I'm usually here earlier and stay later, but can definitely say that I'll be there in that time frame. Okay? I might have gone for lunch or something weird, but I'm around. Okay? So if you want to come see me tomorrow, then you can text 250-864-8386 to make sure I'm there. I would hate for you to make the trek over to the C building. My office is C104, only to realize that I'm not there. So you can just text me beforehand. You know what that means, guys? Spring is coming. Probably not, but the geese are here, so phew. We can pretend. And also, I have office hours Wednesday, 9:30 to 11 or something weird. But I'll be there until class. So you can stop by then. Yeah. Oh, good question. Thank you. Bonus points. Midterm, yeah, Monday, February 11th. Sounds about right. So next Wednesday we'll do our review class, and then we've got the first test. Creeping up on us. Okay. Any questions before we start chapter 3? No? All right. Here we are, chapter 3. 3.1 specifically is the normal distribution. We're actually going to spend, well, all week talking about the normal distribution. I know you thought you knew everything there was to know. It's symmetric, single mode, right? Single peak. What else could you want to know? Lots. There's lots to know. So 3.1 is on the normal distribution, and I spend a lot of time here because this is what the rest of the course will be based off of. Right? And so even if it doesn't quite make sense today or even next day, right, as we keep working at it, it'll start to make more and more sense, right? But there's a lot of tools that we'll introduce that are linked to the normal distribution. Okay. One side note is that 3.4, we just kind of pop out, talk about the binomial distribution, and then we'll come back into this. So it'll feel like we left it in the dust, but we're actually going to come back to it. It's just how the textbook's laid out. It's weird, but anyways. There's a textbook? Well, sort of. I'm just following the sections. Then I blab my own stuff. So, let's do some recalls. So if we have a normal distribution, we've already established that we should be using the mean and the standard deviation as our measures of center and spread. Right? So we've got that under control, so we can write that down. So recall that if we have a normal distribution, we should use the mean and standard deviation which I'm going to officially abbreviate SD here because we'll talk about the standard deviation a lot today, as the measures of center and spread. So that's okay. So it gets a little bit confusing. I know I say that a lot, but until you've got a handle on it, right? Chapter 2, I'm going to call probability. But the thing is, we're going to be dealing with probabilities for the rest of the term, right? Just different probabilities. So not this P of A, P of B stuff, P of A and B, all that kind of stuff. We're kind of leaving that behind. For us, probabilities we're going to use the normal distribution to find these probabilities. Okay? And so, spoiler alert, I guess, the area under the curve, we can use it to find probabilities. In fact, the area under the curve is the probability of something. Right? And so what we'll do is we'll use this normal distribution to find probabilities, but different from chapter 2 stuff. So also recall that we said, right, our notation, because now we're talking about the mean and the standard deviation. We're going to talk about that quite a bit. X bar, remember, is the sample mean, whereas mu is the population mean. Lowercase s is the sample standard deviation, and a lowercase sigma is the population standard deviation. So what we'll do today is we'll just talk about some facts that we'll use about the normal distribution and just develop a little bit of theory, I guess. And then we'll get to the examples next day. So, first fact. Here's a fact. Regardless of what the mean and the standard deviation are, and I'll write this down, but regardless of what they are, if the mean's 1,000 and the standard deviation is 100, or if the mean's 1 and the standard deviation is 2, right? It doesn't matter what scale you're on. The normal distribution is going to be centered on the mean, and we will always only be able to fit 3 standard deviations on either side of the mean before we run out of area under the curve. Okay? So, regardless of the mean and standard deviation, the normal distribution will always be centered on the mean, will always be centered on the mean, and we will only fit 3 standard deviations, and by that I mean population standard deviations, sigmas. And I'll put in here the mean. I'm talking about the population mean. So we'll only fit 3 standard deviations on either side of the mean under the curve. On either side of the mean under the curve. We've already talked about the normal distribution being centered on the mean, right? Because then the mean and the median are essentially the same, right? Because it's symmetric, so it's not pulling the mean in either direction. Right? And so we can draw that out. Try to draw a big normal distribution here. Can be kind of tricky. So this is going to be centered on the mean. That part, that's okay. So whenever you draw a normal distribution, you can just always start by drawing a line down the middle and saying, that's where my population mean is. Yeah. Okay. So that's the first part. The second part is a little bit weirder, right? So the standard deviation is some value, right? Say the standard deviation is 2, for example. Then this is a distance of 2, and then from there we can move out another distance of 2, and then another distance of 2, and then if my curve was nicer, we'd basically have run out of room, right? There's very little room underneath the curve there. So that's what I mean. So we can break up on either side. We can only move out 1, 2, 3 standard deviations until we've kind of run out of room. There's still room in the tails, but it's not large enough to care about. Or maybe we will care about it just way later. So what we have is we have kind of 1 standard deviation, 2 standard deviations, 3 standard deviations. So here we've moved to mu plus sigma. Here we've moved to mu plus 2 sigma, right? 2 standard deviations, because now we've moved a distance of sigma and then another sigma, right? 2 sigma. And then if we move another sigma, we've moved out to 3 sigma. Regardless of what the mean and the standard deviation are. So then here we've moved to mu plus 3 sigma. We can do the same thing on the other side of the mean. It behaves the same way. So here we've got mu minus sigma, mu minus 2 sigma, out to mu, oops, so I should do the same thing. Mu minus 3 sigma. Has anyone heard of 6 sigma? It's a secret society. No, it's not. It's a business thing, and I don't actually know, or I have looked it up, but I don't remember what it is. I think it's like an efficiency thing. 6 sigma. They try to kind of run under some philosophy, and it has to do with this, right? Most of your curve is captured in these 6 standard deviations. Doesn't help when I don't know what 6 sigma is, but that's what it's about. You've captured most of your curve within 6 standard deviations. Okay. So this area here, let's look at this side because it turned out way nicer than this side. This side's a joke. Here. There's a little bit of area here, and I already gave it away, right? The area under the curve is a probability. And so, for example, the mean cuts this curve in half, right? And so if this is a probability, the area under the curve, the total area under the curve must be 1. Right? Looking at all the possible outcomes, the total area under the curve is 1. This area here is just very, very small. So what that tells me is that the probability of being beyond this point, right, 3 standard deviations below the mean, the probability of that is very, very small. Right? And so that's how we're going to use it. It doesn't matter if that didn't make sense now, because we'll talk about it a lot, right, and kind of rehash that idea. But that's where we're headed, right? To be able to look at something like this and say, oh, I landed out here, then the probability of seeing something even further out than that is very small. So let's talk about some more LFFs, little fun facts. More LFFs. Little fun facts. first one is that these tails on either side actually keep going from negative infinity to positive infinity. And the weird part is that these tails never actually close on the axis. So they never close. And if you think about the area under the curve as a probability, right? If they never close, it's leaving a little tiny probability of these weird things happening, right? These very, very extreme things, meaning it's possible, but it's not very likely, right? So it's possible that pigs fly, but very, very unlikely, right? So it's just leaving room for these kind of extreme things. So the tails of the normal distribution extend from negative infinity to positive infinity and never close on the axis. And never close on the axis. Okay. Second one, we've already talked about it, but the area under the curve is a probability. So the area under the curve is a probability. Third one, we've also already talked about. The total area under the curve is 1. The total area under the curve is 1. Okay. To me, that's kind of a mind-boggling thing, right? Because we said, okay, well, sure, these tails extend from negative infinity to positive infinity, okay? And they never close on the axis, but somehow, through calculus, we can prove that the total area under the curve is still 1. It's weird. But for us, we just take them as facts, right? There's proofs behind it, but we're not going to do them. So I don't know. I find that a hard concept to kind of wrap my head around, but it's just a fact for us, right? And so the total area under the curve is 1. The last fact that we'll kind of jot down is kind of obvious, but also a fact that we use a lot, okay? And that's the fact that the normal distribution is symmetric about the mean, right? So if I find that a value is 2 standard deviations below the mean, right, then I can use that fact to find the value that's 2 standard deviations above the mean, right, by just symmetry. So the normal distribution, oops, the normal distribution is symmetric about the mean. And that's what lets us say, so that's what lets us look at this and say, okay, well, if the total area under the curve is 1, right, and this is symmetric about the mean, right? Then the probability of being less than the mean must be 0.5. And the probability of being more than the mean is also 0.5. Right? So knowing one means we know the other, just like the complement. Okay? So we use that fact a lot, that it's symmetric. So, any questions so far? Yeah.
What do you think on the outside of the standard deviations in alpha?
2, but yeah. So, and we'll talk about it. So, for us, right, we use the area under the curve to find probabilities. And so one tricky part, if we look at this, looking at this area, so imagine these as little diced up puzzle pieces, right? This area, whatever it is not going to be the same as this area, right? Even though we've moved out one standard deviation in each situation, right? So this distance is the same as this, it's the same as this, right? But this area is not going to be the same as this area. So we need tools to deal with that, because those aren't going to be easy to find. Well, they will be once I show you. Okay. But we use the area under the curve. We use the area under the curve to calculate probabilities. So like I said, we will be dealing with probabilities, but not in the same way as chapter 2. So it's not important, but if you have your formula sheet kind of handy, what we will be doing later on is we'll use this, the first table that I've given you, table A. So Z table. We will be using this table to find more refined probabilities, okay? Just to give you a heads up of kind of where we're going. But what I want to do first is give you a rough guideline, so an approximation for just quickly finding areas under the curve, right, without using the table. Okay? I actually think using the table is a little bit archaic. It's like, okay, so then we have this, right? And when our phones can do it, R can do it, right? So we have other means of finding these probabilities, but it's my job to teach you this, and so here we are. And so on the assignment and on the test, yeah, I'm expecting you to use the Z table. Okay? But I do want to show you just a quick way to approximate these areas, because that's always good to know as well. Okay? So that's where we're headed, but not until next day. And if you don't have a copy of the formula sheet, you can grab one after class. Okay. So to approximate areas under the curve, we're going to use the 68, 95, 99.7 rule. Catchy. To approximate areas under the curve, we use the 68, 95, 99.7 rule. It has a name, don't worry, it's called the empirical rule. But really, if you Google 68, 95, 99.7 rule, it'll come up with everything you need to know and more. AKA, also known as the empirical rule. I like to call it the 68, 95, 99.7 rule, just because that is the rule. Okay, so without showing you anything, 68% of the curve is captured within 1 standard deviation from the mean. Right? So if I go down 1 standard deviation and up 1 standard deviation, I've got the central 68% of the curve. 2 standard deviations, I've got the central 95%. 3 standard deviations, I've got the central 99.7%. Basically all of it. Not all of it, but basically all of it. And so it's just a quick way of saying, okay, well, I know between the first standard deviations on either side of the mean, I've got the central 68, 2 standard deviations 95, 3 standard deviations 99.7. Okay. Now to draw this gets a little nasty because I still haven't figured out a way to draw the 68, 95, 99.7 so they overlap. So here we go. If you can figure out a way to draw this nicely on one graph. I used to draw 3 graphs. When it gets boring, then let me know. But I've taught this course a lot, and I still haven't figured out a good way to represent it. So there we go. So we've got a normal distribution. Like I said, whenever you draw a normal distribution, just go ahead and draw the mean on here. You know. Okay. And then what we're gonna do is we're gonna dice up our, just like we did earlier, right? Mu minus sigma, mu minus 2 sigma, mu minus 3 sigma, and then up mu plus sigma, mu plus 2 sigma, mu plus 3 sigma. I just figured out a way I could do it, but it's gonna get really messy. But I won't do it. I'll show you guys though, so see how you like it. The 68, right, says that, okay, from the mean, if I move out 1 standard deviation on either side, the area here between these 2 points is going to be 68% or 0.68. Right? When we're doing calculations, we like to work with the decimal, but for me, whenever I'm talking about these areas, I end up doing percentages. So we have to kind of be flexible there. But here, between these 2 points, this area is 0.68 out of the 1, right? Out of the total area of 1. So let's put that on here. So we've got 0.68. Just knowing that, right? Knowing that this total area is 0.68, I can find all kinds of areas, right? I can find the area between mu and mu minus sigma, right? Because it's symmetric, right? So like I said, we use that fact a lot because if it has to be symmetric, then I can just split this 0.68 and this sliver would be worth 0.68 divided by 2, and this would be 0.68 divided by 2. So I can find those areas individually. And that's what, so what I want you to start doing is to think of these pieces as little puzzle pieces. Right? So it's going to be helpful to draw out the area that you want or are looking for, and then figure out what puzzle pieces make that happen, or what puzzle pieces can you take away to make that happen. So knowing that this area is 0.68, we can find this area from here, from mu minus sigma down. We can find that area because we know the total area is 1. So if the total area is 1, we can take away 0.68 to get us to 32. But that 32 has to be split evenly between these two tails. So now we have 0.16 here, 0.16 here. Jot that down in another example. But just knowing that the central, right, 68% is between 1 standard deviation from the mean, down and up, that tells us a lot about these probabilities. Let's try this. So now if we move out 2 standard deviations, we've covered the central 95% of data. Right? So just moving out 2 standard deviations from the mean, we've captured a lot of the data, right? 95% of all the things that we're expecting to see happen, they're within 1 standard or 2 standard deviations. Right? So you don't have to go very far to capture all your data, or most of your data. And then finally, 3 standard deviations, 0.997. I've been drawing these tails, they look huge, but they're not actually, right? Because the same way that we found the area in the tails from 0.68, we can do the same thing for 0.997. So between here and here, we've got 0.997. So that means we've got 0.003 left over, right? It has to total 1. That 0.003 has to be split evenly amongst the 2 tails. Right? So each of these tails only has 0.0015, right? Or 0.15%. It's really, really small. Right? So between here and negative infinity, there's only a 0.15% chance, right, for 0.0015 probability. Same thing on this end. So what that's telling us is that going beyond 3 standard deviations on either side, it doesn't matter if you go down or up, it's very unlikely, right, to see that. Cool. So how do we summarize this in words? The central 68% of the curve will be captured within 1 standard deviation from the mean I'll stick with from the mean. Same idea, right? The central 95%, here I'll just clarify, 0.95 out of 1. Same thing, 0.68 out of 1. Central 95% of the curve will be captured within 2 standard deviations from the mean. And then of course, same thing, 99.7 the central 99.7%, right, or 0.997 out of 1. Oops. Of the curve will be captured within 3 standard deviations. From the mean. Right. So that's just this image in words. So our goal in this course is going to be to assess whether something is extreme or not. So overall, big picture, our goal is to assess or analyze if a value is extreme or not. If a value is extreme or not. For example, if you're comparing your sales numbers, let's say, to your colleagues, what you're really trying to show your boss is that you, right, the number of sales that you make is extreme in comparison to your colleagues. Whatever you want to measure, sales probably in dollar amounts, right? So the amount that you're bringing in dollar amounts is extreme in comparison to everyone else. The number of billable hours that you have is extreme in comparison to other people, right? Let's say you've developed a drug and the effects of your drug are extreme in a good way, hopefully, compared to other drugs out there, right? So that's kind of the moneymaker, is being able to say, no, this is extreme, right? And what we're doing and why you have to take this course is because I'm going to show you how you show that things are extreme, right? And so you'll be able to say, my sales are extreme in comparison to my colleagues, right? Because of this calculation. So that's where we're headed. As a general rule, as was foreshadowed, anything that's more than 2 standard deviations away from the mean on either side will be considered extreme. And just like we have the 68, 95, 99.7 rule for approximations of areas under the curve, and then we'll use the Z table to get more refined areas under the curve, same idea. We're going to use 2 standard deviations away as a guideline, right? But then we'll develop more refined tools for deciding if something's extreme or not. But honestly, if the one thing that you take away from this course is 2 standard deviations is extreme, that's good. Then I'm happy. What? That's it? Great. I know it's a little bit more than that, but in the grand scheme of things, right, as long as you remember, okay, 2 standard deviations, that's extreme. That's good. So as a general rule, we say that a value I'll start with within the central 95% of the distribution is not extreme, right? That's where 95% of everyone's hanging out. That's completely, I hate to use the word normal. When we're talking about the normal distribution, gets confusing, right? But that's the norm. Let's say that. So that would be not extreme. Anything beyond that, though, would be considered extreme. So anything within the central 95%, 95% of the distribution will not be considered extreme. I guess we could call it the complement of that, opposite of it, is that if a value is more than 2 standard deviations away, away from the mean, that's either above or below. It doesn't matter which direction it's going, above or below. We consider it an extreme observation. We consider it an extreme observation. All right. We have to be able to find how many standard deviations things are from the mean. Sounds important, right? If we have to be able to say, well, if it's more than 2 standard deviations away, it's extreme. So we need some way to figure out, okay, well, how many standard deviations from the mean is this value? And so this means we need to be able to calculate how many standard deviations a value is from the mean. Let's say for a brief example, I'm going to tell you that the mean is 6 and the standard deviation is 2. And ask how many standard deviations is 4 from the mean. That's fine, right? We can kind of handle this, right? We can say, okay, well, 4 is a distance of 2 from 6, right? And you can kind of visualize it by doing just a quick number line here. You have 6 and then you plot 4 on here. This distance, oops, too far. Right, that distance is 2, right? And because a standard deviation is 2, right, I've fit 1 standard deviation in here. So therefore, 4 is 1 standard deviation below 6. So we can kind of do problems like that. Let's do one before I give you the formula that we can use. So say the mean is 6 again, and the standard deviation is 2. How many standard deviations is negative 4.91 from the mean? We can think about what we're actually doing in the first example, right, where it seemed so reasonable. We're saying, okay, well, and maybe it still feels reasonable, I don't know. But between here, 6 and negative 4.91, we want to find how many times can I fit 2 in here. We could go 6, down 2, make a notch down 2, make a notch down 2. It's not going to end up looking that nice though, right? So at some point we have to remember here we've crossed 0, right? And so this distance is actually 10.91. Right? So this distance is the amount that we want to divide by the standard deviation, right? How many times can I fit a standard deviation of 2 into 10.91? So this is the distance, right? And so what we're finding is we want to take the distance divided by the standard deviation. So we do 10.91 divided by 2, which makes 5.455. That's hard to arrive at if you're just trying to figure it out by kind of bunny hopping down, right? And a little bit unmanageable in the end. And so what we have is this formula, which is called the Z-score. And the Z-score tells us how many standard deviations X is from mu. Okay? So to calculate how many standard deviations, right, and I'll put sigma in brackets there, a value, right, or observation, which we'll denote by just the lowercase x, is from the mean, mu, we find the Z-score. And the Z-score, it's on your formula sheet, but I'll just write it on here, x minus mu over sigma. But I wanted to show you those 2 quick examples, right, where you kind of have to figure out how you're doing it in your head, just to show you that x minus mu is actually just the distance over the standard deviation. So we're doing the same thing, but now we have this kind of machine to calculate how many standard deviations X is from mu. Right? And so for us, so Z is X minus mu over sigma. For us, we had an X of negative 4.91 and a mu of 6 divided by 2. That's negative 10.91 divided by 2, which is negative 5.455. That's the same value. It's negative because it's saying, oh, and by the way, negative 4.91 is below the mean, right? So the negative is saying it's 5.455 standard deviations below the mean, right? Whereas if it's positive, it's saying it's above the mean. And so here, a negative Z-score means X is below the mean. Whereas, of course, a positive Z-score means X is above the mean. So Z equal to negative 5.455 says X equal to negative 4.91 is 5.455 standard deviations below the mean. Mic drop. See you on Wednesday. Had to squeeze it all in there. That. How about more? There? Good. And a positive Z score means it's above. Yeah, I was just doing the whole deal. Oh, I think she was like, yeah. You guys and it was like laid out the same way and everything. It's like you guys are mind players. Yeah. It's like you guys should look at it. And I was like, that's how like I'm like, oh, this thing twice. Don't worry. I'll plug it out. Don't worry. I know that's what she said. She's like, I don't know math yet. I was like, oh, weird. Yeah, exactly. Like kind of funky type. Yeah. Oh yeah, even our things that exactly. That's. I was like, you guys are like mind buddies. Yeah. Oh, I'm gonna make a photocopy of this one. Who needs assignment 2 still? Just 3? Okay. I'll get some photocopies here.
Would you have them by like 100 dust tomorrow by chance?
Oh yeah.
Okay.
Yeah. Yeah, if you want to do that.